Hello. Yes.
Okay. Am I audible, Sister Navina? Sister Navina.
You are audible, ma'am. Good afternoon, ma'am.
Hello.
Sir, good afternoon, sir.
Very good afternoon, ma'am. I'm sorry for my late, and I'm little bit busy with some other program. First of all, good afternoon to everyone.
Good afternoon, sir.
I am
Sir.
honored to be here, part of this webinar, addressing the distinguished people.
Sir.
Is it audible, ma'am?
Sir.
Hello.
Sir.
Is it audible, ma'am?
Yes, sir. Audible, audible.
Very good afternoon to one and all, ladies and
Sir,
gentlemen.
1 minute. Sir, 1 minute. We will invite, sir. Just begin with the introduction. A pleasant good afternoon to all. On behalf of the management of Jmj College for Women, Tenali, I, Dr. N. Vimla Devi, Head of the Department of English, extend a warm welcome to each one of you for this one-week international Webinar-cum-Faculty Development Program on recent advances and future trends in artificial intelligence. Is it audible? Is it audible? Pleasant good afternoon to all. Is it audible? On behalf of the management of Jmj College for Women, Tenali, I, Dr. Vimla Devi, Head of the Department of English, extend a warm welcome to each one of you for this one-week international Webinar-cum-Faculty development program on recent advances and future trends in artificial intelligence and cyber security. Let's begin our webinar with a prayer song by Sister Navina, a student of First BSc Mathematics, to improve God's blessings for the fruitful session. Sister Navina, let's begin our webinar with a prayer song by Sister Navina.
I come before you today, and there's just one thing that I want to say. Thank you, Lord. Thank you, Lord, for all you given to me, for all the blessings that I cannot see. Thank you, Lord. Thank you, Lord. With a grateful heart, with a song of praise, with an outstretched song, we bless your name. Thank you, Lord. I just want you. Thank you, Lord. Thank you, Lord. I just want you. Thank you, Lord, for all you've done in my life. You took my darkness and made me your light. Thank you, Lord. Thank you, Lord. With a grateful heart, with a song of praise, with an outstretched song, we bless your name. Thank you, Lord. I just want you. Thank you, Lord. Thank you, Lord. I just want you. Thank you, Lord. Thank you, Lord.
Thank you, sister. Dear participants, I kindly request you all to mute your audio and switch off your video during the session to avoid inconveniences. If you have any questions during the presentation, please feel free to post them in the chat box. The doubts will be clarified, and when necessary, your cooperation in this regard is greatly appreciated. A heartfelt welcome to our correspondent, Dr. Sister Teresamma Gade, Dr. Sister Shaini KP, the principal, our esteemed guest speaker, Sri P.S. Surya Prakash Rao, Joint Secretary to Governor, Andhra Pradesh, and today's resource person, Mr. Rex Arokya Swami, the Senior Systems Analyst, UST Global Services, Atlanta, US, Mr. Richard Rex from Georgia Institute of Technology, Georgia, and all the participants who are joining us for this webinar. A warm welcome to you all. Today, we have a special guest, Sri P.S. Surya Prakash Rao, Joint Secretary to Governor, Andhra Pradesh, to address us with his warm greetings. Let us welcome him with great honor and respect, Dr. Vimla Devi, Head of the Department of English, to brief about Sri P.S. Surya Prakash Rao, Joint Secretary to Governor, with the words of welcome. Welcome you, sir. Sri P.S. Surya Prakash Rao, Joint Secretary to Governor, has completed his Master's degree in Psychology and Master of Arts in Public Administration. He held various posts in Andhra Pradesh state level, like Chief Executive Officer, Jilla Praja Parishad, Krishna District and Guntur Districts. Personal Secretary to Minister for Endowments, Assistant Director for Treasuries and Accounts Departments, Kakinada. Chief Accounts Officer for Prohibition and Excise Department, Kurnool. He has achieved many awards like Best Employee Award from Collector and District Magistrate, 3 times in the year 2021 and 2022. Best Employee Award for Outstanding Services during COVID-19. Best Employee Award for the meritorious work done on 26th January 2020. Award received from Honorable Chief Minister of Andhra Pradesh for National Deen Dayal Upadhyaya Grama Swashaktikaran in the capacity of Chief Executive Officer, Krishna District, and received cash prize of 50 lakhs to the Jilla Praja Parishad, Krishna District. Best Officer Award for the excellent work done in Manam Mana Parishubhrata by the Minister of Panchayat Raj and received 10,000 rupees as cash award. Hearty congratulations, sir, on behalf of Jmj College for Women, Tenali, for your outstanding achievements. Sir, we are extremely happy with your presence. We welcome you once again to grace this wonderful session.
Thank you so much, ma'am, for your wonderful introduction. And I am very much honored to be here, part of this webinar, addressing the distinguished people like you all. First of all, let me congratulate and convey my heartfelt greetings to Jmj College for Women, Tenali, for conducting this webinar for 1 week. I think conducting this webinar for 1 week. I think this is an online webinar program, international Webinar-cum-Faculty development program on recent advances, future trends in artificial intelligence and cyber security. I think it was started in on 14th November. I think I also participated in that webinar. This is the last day, I think. Knowledge is ocean. Learning is a perennial process, and we should learn every day until our last breath. Without learning, we can't earn anything. In this era of technological advancements, artificial intelligence stands at the forefront, reshaping the landscape of industries and societies. Artificial intelligence, with its ability to process vast amount of data and derive meaningful insights, is not just a technological marvel, but a catalyst for transformative change. It has penetrated diversified fields. So many fields now artificial intelligence very much important. From healthcare to finance, revolutionizing how we approach challenges and opportunities. As we delve into intricacies of artificial intelligence, it is crucial to emphasize the ethical considerations of that accompany or its rapid development. Responsible artificial intelligence practices ensure that the benefits are shared equitably and that the technology aligns with our collective values. I think collaboration and knowledge sharing are paramount in navigating the complexities of whatever it may be. Right now, we are talking about artificial intelligence. Webinars like this serve as a crucial platforms for fostering dialogues or fostering innovations or taking so much knowledge and ensuring that the benefits of artificial intelligence are accessible to all. Let us embrace the possibilities that artificial intelligence brings while remaining vigilant about its ethical implications. Together we can shape also an artificial intelligence driven future that prioritizes inclusivity, transparency, and ethical considerations. The main ethical consideration is very foremost important in this aspect. because artificial intelligence includes all. Once again, I have known nothing actually for regarding artificial intelligence, but I learned something after attending this webinar actually, because I am from art student, arts background. I am an art student, but I am very much enthusiastic to know something about the upcoming artificial intelligence. I learned something, but I have to learn so much thing, so many. Thank you for having me, and I look forward to the insightful discussions in this webinar. Once again, my sincere greetings to our organizers, and as well as my sincere namaskarams to Arigya Swami sir, today's uh, lecturer, and as well as all the participants. Thank you once again. Thank you, Vinod.
Thank you, sir, for accepting our invitation to address the participants. It was a great honor for Jmj College, especially to the Department of Computer Science. When I saw your registration for this international Webinar-cum-Faculty development program, I thought that this online platform have brought many of the research scholars, faculties, and knowledge seekers under one platform. So I too thought that you are a knowledge seeker always. So it is indeed a blissful moment for our Jmj College for Women with your presence. Thank you. With your busy schedule, you have spent your valuable time with us. Thank you for addressing the participants, sir. Once again, I express my thanks to you, sir.
Most welcome, ma'am. Please let me know whenever you conduct these webinars on whatever topic, no issue. Definitely, I'll be one of the participants.
Sure, sir. Thank you, sir.
Thank you so much, ma'am.
Thank you, sir. Dear participants, it's my pleasure to introduce our speakers of day 7. Mr. Rex Sarakasamy, the Senior System Analyst, and Mr. Richard Rex, Master of Science in Georgia Institute of Technology, United States, who will be sharing their knowledge and insights on the topic machine learning techniques, trends, innovations, and real-world applications. Mr. Rex Sarakasamy currently working as Senior Systems at UST Global Services, Atlanta, Georgia, United States, a company that provides digital technology and transformation, information technology and services. He formerly worked as Assistant Product Manager at UTech Cybernetics Chennai and Architect at Wipro Technologies Bangalore. He has a wide range of expertise in software development, software architecture skills, and architecture solutions, including automotive infotainment, banking domains from 2007 to till today, about 16 years of experience. He has served for various clients in numerous domains, including infrastructure management, retail, and delivered solutions for different technologies, architecting, project management, analysis, design, implementation. He has trained multiple clients for various projects. Sir will be dealing with the introduction part of the machine learning techniques. May I request Rex sir to begin the session.
Thank you, Reverend Sister Amul Mary.
Thank you, sir.
So let me start. It was a great pleasure to join the webinar conducted by Jmj College. So for the last 60 years, it is shaping the betterment of the students, and it has shaped the life of hundreds and thousands of students. Very happy to speak among you the staff members. You have made the college not just leading in the state, but in the entire country itself in the top rankings. So it's a great opportunity, and I'm very thankful for Sister Amul Mary, management, and staff members for inviting us for a short talk with you. It is a great, I'm very grateful for the sisters, because I know when I was admitted into the first standard, I still remember Reverend Sister Nirmala. When I was sitting in the class, she has to cut a piece of cloth from her apron for wiping my nose. So sisters made a huge sacrifices for the education and other things. I'm very thankful, because for what I am today, sisters like you have lighted the families of hundreds and thousands of people. So for this topic, Richard will present the machine learning, artificial intelligence, and its applications. But I want to touch a few things before going into this topic. As a teaching staff members, you are not just shaping the students, but you are shaping the entire country. So you need to be visionary. After the independence of India, India was poor. Then Prime Minister Jawaharlal Nehru, he has created IITs, IIMs, All India Institute of Medical Sciences, and plenty of other public sector companies, because he wanted to develop the country. But what he might not have imagined, these people who are the products of IITs, IIMs, they will shape the country, they will develop the economy, they will take the entire country to the development path. But what they might not have imagined, these people, they go into the global stage, like Sundar Pichai. He is the product of IIT, or the former PepsiCo chairman Indra Nooyi, or plenty of other CEOs in US. They are taking the entire humanity or the entire world towards the development path. So we need to be visionary. Just two things as a staff members, what I expect, we have to continuously upgrade ourselves to meet the future challenges. See, there are people who are developing the solutions for the complex problems of today's and future, but you are developing the students themselves. They are going to develop the solutions for the problems. So you have the great responsibility on your head. So I'm very thankful to have a few minutes with you. So first we have to upgrade continuously to stay, not just to stay afloat, but to keep learning the technologies, because we have the tools and chains that's evolving. So we need to be up to date to make ourselves to find the solutions for the problem, and then creating the students, preparing them to meet the challenges. Innovation is a key portion. So innovation is not something everyone has to invent, like aircraft or other high technology solutions. It's in the mind. There was a problem in a very reputed soap manufacturing facility in Japan. So they have started receiving some complaints from the consumers when they purchase some pack of soaps at home. When they try to open the boxes, small boxes is empty. When the company is trying to find out the root cause of the problem, so it is in some of the machineries, by some software mistakes, it's started packing some empty packs. There are people, they were thinking of finding solutions which might be time consuming. But what the thing, one of them came with a proposal, they have installed a big pedestal fan on the pipeline of the soap manufacturing facility. So if there are some empty boxes, with the air blowing from the fan, they have been removed from the pipeline. So only the quality items have been packed in the boxes. So that's the kind of innovation. So everybody, we are capable of finding solutions and think the out of the boxes. I think the artificial intelligence, it is not something which has come today or a couple of years. We've seen for last couple of decades, it has been developing either by aware or unaware. It is part of our life. So only thing is the days and the coming months and years, it is going to decide to what extent it is going to affect our human life. Computer is not a precious thing anymore, because I remember when we have started working or teaching the computer science, maybe 20 years, 25 years before that, that used to say Indian computer science teachers are the best in the world. Why? Because they only can teach computer science without showing the computer itself. It is not the case today. Governments across the different states, they are distributing free laptops to students. So everybody has access to the computers. Even the car which you are sitting and driving today, that has 50 plus computers on it, all of them talking to each other. So as an advanced, when we turn on or when we watch some YouTube videos, next time it understands our habits. It suggests what are all the things which suits our interest. It is suggesting ourselves. Or when you are trying to start your car on an usual day to the college or return from college back to home, the Google or Apple applications, navigation applications, it suggests the estimated route and the travel time to your home, and which is the best route you can take it. So it is already part of life. But there are many things which you might have learned in the past or in the last 1 week, the technological advanced things which is going to hit the market and our daily lives. So one of them is automated car from Tesla, which is already there in the many test drives. So you don't need to worry about learning, just sit behind. It is going to drive itself. It is going to monitor the signals. It has radars to watch what's coming behind or the sides or in front of you. So it know when to start, accelerate, things like that. Also, in the last 1 week, you might hear some disturbing things like deep fake videos emerging, and plenty of such challenges, problems that are going to come. So we need to upgrade ourselves to meet the challenges. That's the intention. So thanks for our distinguished guest, Mr. Surya Prakash Rao, and all our staff members. So with a brief introduction, let me invite Richard to share the presentation on this machine learning applications. Yeah, thank you all. Thanks for giving me an opportunity. Over to you, Richard.
Sir, thank you, sir. Thank you, sir, for your great admiration towards the missionaries, especially sisters. And you have also advised the faculty members to prepare the students for future key posts like, and the introduction about machine learning techniques. Thank you, sir, for all your guidance to me for this 1 week webinar, international webinar. Thank you, sir. Now we have Mr. Richard. He has completed his BSc in Computer Science and MS in Computer Science at Georgia Institute of Technology, United States, who secured 4 GPA out of 4 and secured award from Dean's List University. He has completed various courses on data structures and algorithms, machine learning, software engineering, computer organization and assembly, linear algebra, abstract vector spaces, graph theory, probability and statistics, natural language processing, number theory, machine learning, high performance computing and architecture. He is also familiar with various programming languages like Julia, Python, JavaScript, C, C++, Java, TypeScript, SQL, Dart, HTML, CSS. He is also well versed with frameworks like NumPy, Scikit, TensorFlow, Keras, PyTorch, Pandas, and many other languages. He has completed projects on cloud computing, high performance computing simulators, Tesla, peer professors. He also conducted comprehensive data analysis on large scale mortgage datasets for machine learning research intern on Ameriserve mortgage for an abort of 3 months Georgia. Also implemented cloud agnostic storage feature for ML API built on Fast API for software engineering intern at San Francisco. He is currently pursuing research on seismic laboratory for imaging and modeling in distributed machine learning at Dr. Felix Herman's lab, Atlanta, US. Sir, we appreciate you for your academic profile and vast knowledge in programming skills. We hope that you will enlighten the participants with your knowledge. Over to you.
Thank you, Reverend Sister Amul Mary, and all the organizing faculty of Jmj College. Just like to thank you for this opportunity. I hope this lecture is actually beneficial to all of you. So I'm going to share my slides.
Yes, sir.
Okay. So can everyone see my slides?
Yeah, can see.
Some confirmation in the chat. Okay. All right, so we can start with. All right, everyone. So today I'm going to be talking about artificial intelligence and machine learning. So this is a very broad topic. So I'm going to try and narrow it down and make sure everyone understands the holistic field and where it's headed and the different components that make the field really, really popular. And so let's get started. So start with a bit of background about myself. So I'm currently a master's student here at Georgia Tech, specializing in machine learning. I'm also doing research as part of my coursework. So I'm working on a scalable matrix-free abstraction for machine learning and also inverse problems. I've also interned at a couple companies. First one is a machine learning company which are developing an alternative to cancer imaging. And the second one is a mortgage company where I automated some of their workflow using machine learning. So if you guys are interested in learning more, I encourage you to ask some questions at the end. So I'll also be monitoring the chatbot. So if you have any questions throughout the presentation, please feel free to put them there. I do prefer more of like a discussion driven lecture. So we're going to do a quick overview of artificial intelligence, a lot of level setting, and we're going to do a quick deep dive onto several components of this. Given the amount of time, we can't do the deepest of dives, but just enough for to understand what's going on. And we can certainly stop for philosophical questions towards the end, but any questions regarding the slide deck, please feel free to interrupt me. So what is artificial intelligence? So this is a question that actually takes a lot of time to come up with, and this is here is a good definition for what artificial intelligence is now. There are two main aspects to this. First is the concept of narrow AI, and the next is the concept of general AI. Sometimes in conversation, we tend to conflate or mix the two. So narrow AI, according to this definition, is the theory and development of computer science systems that perform tasks that augment for human intelligence, such as perceiving, classifying, learning, or some reasoning task. And general AI, as we define it, represents full autonomy, emerging from the convergence of three big scientific communities, namely big data, compute technologies, and machine learning algorithms. And a very critical driver between AI's growth is the commercial viability, ranging from advertising, image recognition applications, to autonomous driving applications. So why now, right? So AI has been around for about 5 to 6 decades, but why is AI really popular now? And AI today has become extremely popular because of three main scientific communities. First is big data. The vast amount of data that is available now makes most of these algorithms plausible. So a huge reason for this is the internet and the growth of social media platforms and the growth of personal devices. So there's just so much more data than there was before. Secondly, we have compute. We have compute that is undreamt of. So according to Moore's law, the compute has been growing almost exponentially. So we also have the growth of algorithms. So algorithms tend to be something that aren't as quickly evolving in other fields, but in the case of machine learning and AI, it is growing just as fast. And I'd like to point out that compared to software engineering or computer science in general, the field of AI grows about like twice as fast. So if there's a new way to do anything in computer science every 4 years, there's a new way to do that, something in AI every 2 years. But AI today is not just about these, right? It's about a comprehensive system. And understanding what goes into the system is crucial. So we consider AI structure as a canonical architecture. This is an end-to-end pipeline that encompasses various components and their interconnections. So as you can see, the architecture here spans from sensors to end users or missions for some downstream tasks. So this integrates multiple steps from data acquisition to final application. So we start with data collection, either structured or unstructured, followed by data conditioning or curation. And post-curation, this data is transferred into information, which is then processed to one or several algorithms, which leads to the creation of knowledge. This knowledge is then integrated into some human-machine teaming module, which gives you actionable insights for specific missions. And all of these components are underpinned by modern computing technologies. So this takes into account for all the hardware elements accessible to us. So I'm going to talk about some of the components on here. So starting with robust AI. Robust AI is essential, right? It encompasses the explainable AI, bias assessment, verification, validation, security, and all policies that regard this. So an example is, let's say you are building AI that's going to be used by a bank or a mortgage company, which determines your criteria for getting a loan. You want this AI to be explainable, and you want it to give you sort of a spectrum of explanations for why a given decision was taken. And all of these account for robust AI. In the case of autonomous driving, you want AI to be reactive. You want it to be fast. And you define robust AI through a lot of metrics that are constantly evolving. The history is, however, very rich and varied, right? And this is marked by significant developments and AI winters, which reflects the evolving understanding of these technologies. So in the traditional viewpoint, AI consists of three sort of big waves, 3 or 4 big waves. The first wave is, you can think of the first decade of AI technology, which is a result of a lot of reasoning-based systems, which were based on handcrafted knowledge. An example of this are like expert systems. So a lot of work went into these expert systems. So take the 4 dimensions, which is the ability of a system to perceive, learn, abstract, and reason. So these are typically pretty good at reasoning because they encode human knowledge. So a human expert sat down and encodes these 4 rules. For example, take tax software. So, for example, an expert system does a pretty reasonable job on that, where a chartered accountant or a tax expert encodes their rule set into the system. Some of the early autonomous vehicles used these forms of expert systems where the states on the finite state machine were handcrafted, and the transition between them was designed in a certain way. As you can think about, these are not very adaptive, right? So this was the first wave of AI, and there were a lot of machine learning wrapped around this, but they definitely played a large part in autonomous vehicles. And over time, we were able to use these expert systems, and they're still extremely valid, right? So you have cases where they're limited data, a limited compute power, and so a lot of expert systems are still being used. And since they're explainable, that makes it robust. They can typically point to a set of rules that somebody wrote and explain their decision based on that. But as we were able to collect more data, we were able to understand a little bit more about what the underlying process was. We were able to apply statistical learning, and this led to the next wave of AI, which is often called the learning wave. And this was the key enabler here was just data, right? And what we mean by that is we were able to dial back the amount of expert knowledge that we put into our algorithms and use data instead of that. So an example is in speech processing. For example, if we were able to say, well, I kind of realized that speech follows this Gaussian mixture model. So I can encode that level of statistical knowledge, but I'm going to let the system figure out the details of how that actually worked out. And there are many other cases. Coming back to some of the research that went into this, people started steering away from high expert systems and towards learning systems. So looking at the features, these systems had a little bit more on the perception. So they were perception side, meaning they used sensors and information sources. And this was the key driver. So the next wave, which maybe we're at the beginning of, is called the contextual learning, contextual adaptation. I should actually say we're about in the middle of this wave. So this is where an AI system can add context into what it's doing. So most of the work today probably falls into the end stage of the learning wave, but we're able to combine a bunch of these learning processes to make it look like it's contextual in nature. A huge example of this is language modeling, and what people have been doing with huge language models like ChatGPT and so on. I'll cover language modeling later in the slide deck because I know it's so popular right now. So the key concept in this third wave is to abstract and reason in a similar way that humans do. So for example, if I see a chair and I put a chair somewhere else, I still know it's a chair because I'm using other context. Maybe next to a table or something like that, but there's still some context that points to me that it's a chair. And we are embedding this way of reasoning into these machine learning systems. And certainly this wave can be called as an abstraction. There's not huge work into contextual adaptation, but there's a good amount. So that's a little bit on the evolution of AI. So the reason I mention this is because there's great work going on each of these waves, but to understand why what we do now is important, you need to understand what came before. So when people are working on each one of these components, it's typically that people have a lot of dials at their disposal. So the first dial is how much compute do you have, how much ability, which is basically how much ability do you have to crunch data. The second piece is how much data do you actually have. And the third dial is how much knowledge you're able to embed into an algorithm. It's certain cases where people have very little computing, very little data, but not a lot of expert knowledge. People tend to use expert systems. And that's a very good use case of that. And if you have a computing and data available, but you want to encode very little human knowledge, this is where neural networks fall in. They're essentially learning what human knowledge is, that encoded information should look like. A lot of statistical techniques also fall into this camp, but you encode a little bit of information, like what the background distribution of the process is, but it learns the details of how exactly that distribution is modeled. So you have a lot of different settings that you can use, and there are different techniques that lie within the broader AI context that you can use to achieve your goals. So I'm sure many of you have heard of different types of algorithms, and a lot of decision on what kind of algorithms that you pick for tasks are dependent on how much data and the quality of data that you have. So here we have sort of like knowledge-based algorithms, we have transfer learning algorithms, reinforcement learning algorithms, and so on. If you know a certain process behaves in a specific way, you can guide the algorithm to focus on learning that specific distribution instead of trying to learn the broad distribution. So that's the idea of picking algorithms that embed your knowledge. So the father of reinforcement learning, Rich Sutter, actually suggests against this. So he has this theory where he suggests that AI algorithms should not embed our knowledge, but it should instead just leverage computing. And there's actually a good backup for this in historically speaking. If you take, chess, chess was solved by IBM a long time ago, but way before that, chess was being approached by researchers all across the world, and they all approached it in a way where they used specific techniques and opening theory and middle game theory, end game theory to guide their algorithms. But in the end, what turned out to be the best chess system was simply a compute-based brute force system. So it's because compute is growing so fastly, I still believe that compute is the main driver. But algorithms need to get better, even though we have not hit sort of the bottom of the growth of compute. It still gives you better efficiency. So into a bit of more critical components of this AI architecture. So a lot of press may be on algorithms, right? You read a lot of research papers and you notice that the algorithms have been designed, but really the available of a good canonical data set is equally, if not more, critical to a breakthrough in AI. So what we're doing here is just picked a set number of breakthroughs in AI, and we want to make sure that we understand why data is so crucial in such breakthroughs. So the first piece of this whole architecture is data, and we're going to take a look at what data conditioning is, which is basically converting unstructured and structured data into usable format. So within this structured and unstructured data, you might have structured sources coming from sensors, network logs, metadata associated with these sensors, speech, or any other such signal. So these are the structured data. So there's also a lot of unstructured data, things that are just collected from the internet or social media site. And the first step that we do in these architectures is data conditioning, which is basically you want to figure out where to put this data. We're here to tell you that you're probably okay picking most technologies, but typically these infrastructure databases provide better capabilities for storing such data. So we have indexing, organization, structure, and all such things in the structured data can be captured by algorithms. And you want to convert these into formats that you can store in some of your downstream task-based database. So in the context of machine learning, you would spend quite some time of data labeling. So let's say you're Uber and you're building a self-driving.
And that I don't know. I did not realize. However, I
We are making it.
Oh, sorry.
Okay, you can continue, sir.
Okay, no worries. Yeah, so in the context of supervised machine learning, what you want to do is you have these data, and typically they need a lot of labeling. So let's say you're Uber and you're trying to build a self-driving car, and you have about like 10,000 images that your car captured, and you want to figure out if there's a person in the car. So you can then train your cars to understand what a person looks like. And typically how they do this is they outsource these labeling tasks, but this is still a very crucial part. Good data comes with good labeling. You want to do a project that is oriented of how we can leverage this. Sister, I think you're unmuted. I think there's a little bit of static.
Sir?
Yeah, if you could mute yourself, I think that would be better.
Okay.
Thank you. So you want to do a lot of initial data exploration, and this could simply be, opening it up in Excel and seeing what kind of data you have. You might look for errors, bias in the collection, and of course the actual labeling process that you're doing to highlight this is you want to highlight the phenomena that you want to model the phenomena that governs these data. So the question is, what is the ratio of data that exists between structured and unstructured? And in practice, it turns out that unstructured data is about like 90% of the volume of data, maybe 10% being the metadata associated with it. So structured data is actually very little. So there's a lot of potential with unstructured data. So we can talk a lot about the infrastructure and databases being a driver in deciding how we can deal with unstructured data. So the question is, when you apply these AI or machine learning tools to a specific problem, is it typically a single modality or multiple modalities? And what that means is basically, are you using one data, a couple data sources, what's going on? And the answer is both. There's a lot of research on how to fuse multiple modalities of data. As of today, a lot of published work may focus on single modality, but the value lies in multiple modalities. So a lot of the expert systems deal with multiple data sources and work on multiple modalities. And if you take speech, for example, why would speech fall into structured versus unstructured? And this is because it typically comes with some known metadata, which follows a certain pattern, has a clear range, a frequency to which data is collected, and that's why we stuck it in the structured data type like you see here. Of course, if you're collecting it out in the field, it would fall right here. So data is a crucial part, and now I think the next important thing to look at is what is the existing taxonomy for machine learning algorithms. And this is the part I hope everyone's interested in, because after navigating through this vast knowledge base, it's impossible to classify everything. But Lincoln Laboratory at MIT has done a pretty good job at coming up with this taxonomy. So let's take a look at this. So at our very core, our very, very broad layer, we have artificial intelligence, which encompasses all of machine learning. And there are several techniques inside machine learning, like neural networks, Bayesian inference, connectionists, evolutionaries. These are all theories that exist within machine learning. And within those theories, there are sub-theories that learn to do a specific task really well. For example, if we take Bayesians, these are typical algorithm here would be a naive Bayes. And these are all algorithms about probability and statistics, where they make decision boundaries based on the likelihood of certain outcomes. Then we have, so these are the classification of our algorithms here was proposed by Pedro Domingos from University of Washington. He's basically a computer scientist that has contributed to machine learning quite a bit. He suggests there are 5 tribes of machine learning. So the 5 tribes here are symbolists, with expert systems being a prime example of symbolists, where they try to model everything, maybe in a very concrete way. If you sort of wrote machine learning algorithms that involve regex or something like that, you would fall under symbolists. So there are predefined rules and logic to make these decisions. Next, we have Bayesians, which is what I talked about, and these people are statistical people. Then we have the analogizers, and things like support vector machines fall into this category. What they do is they try to find a boundary that separates different categories of data. It's much like finding a balance in a very complex puzzle. Then we have the connectionists, and these are represented by something called deep neural networks, which is this term that is inspired by the human brain. So there are these little things that are inspired by neurons in your brain, and what they do is they try to encode some knowledge that you're trying to embed it with. And the last is evolutionaries, which genetic program is a prime example of. These algorithms are not like traditional machine learning. What they do is they try to mimic the process of natural evolution to generate solutions, evolving and adapting over time. As you can imagine, these are much harder. So each of these, however, has its own strengths and is suited for different type of problems. The key problem in machine learning is how do you match your problem with the right algorithm, with your specific needs, considering stuff like how much data you have, the computational resource that you have, and the type of problem you're trying to solve. So the diversity is crucial to understand, because if you're new to AI, you might think it's all about neural networks. But while neural networks are the specific class of machine learning algorithms that exist in the specific view called connectionists, there's actually a whole wide world which consists of different viewpoints. So if you visualize AI as a large circle, we have within the smaller circle of machine learning, and even within that we have neural networks, and then we have our deep neural networks. So to give you an example of something that falls under AI but outside of machine learning, this is where expert systems would fall. So expert systems are still artificial intelligence, but they're not machine learning. So this is sort of a brief overview of the taxonomy of AI. So let's move on to how is compute an important part of this architecture. So modern computing engines have been pivotal in the AI resurgence over the past few years. So like we know, we're all aware that data, compute, and algorithms are key drivers, but what about the specific technologies that make this possible? For instance, there's different types of compute, namely we have CPUs and GPUs, which are widely recognized computing platforms with extensive software compatibility. However, as we reach the limits of Moore's law, which which basically says that compute available per dollar or per unit of currency should double every 2 years. So despite reaching the limits of this, there's still a growing trend towards performing engineering and development of custom hardware architecture. And these custom architectures are becoming more of a commonplace and the commercial off-the-shelf solution. So if you take, for example, Google's Tensor Processing Unit, this is a custom architecture that is specifically designed for machine learning tasks. It's optimized for very popular machine learning frameworks like TensorFlow and Google's open source machine learning framework, and even newer frameworks like Alpha, which basically deploys these machine learning models at scale. So custom hardware, another example is actually this neuromorphic computing. This field is inspired by the structure and function of the human brain. Unlike traditional architectures, neuromorphic systems often operate without a central clock. So it's clockless, whereas CPUs, GPUs, and TPUs sort of have a clock. So what they're trying to do is mimic the asynchronous nature of your neuron activity. They also integrate unique memory architectures, closely resembling how neurons and synapses work in the brain. So this approach could possibly revolutionize how we process complex, unstructured data and offer an energy efficient and faster method. So for example, the laboratory that came up with this, there's also exciting work on graph processors, which is a custom processor that handles and processes graph data structures, which is increasingly common in applications nowadays. So no discussion of AI would be complete without mentioning quantum computing. So we're still in the very early stages of applications in AI, so the state of art now has very good success in solving linear systems of equations, but its potential is immense, right? Quantum computing basically operates on the principles of quantum mechanics, which potentially allows you to process information at unprecedented speed. So it is a technology that is still unfolding, and its future role in AI could possibly accelerate everything that we've ever known. So when we think about these neuromorphic computing, remember that's about creating a brain-inspired architecture, which is often clockless. In summary, from TPUs to neuromorphic computing and quantum computing, we're witnessing quite a era in computing technologies. Each are playing its own role in advancing AI. And these are not theoretical. These are actually available off the shelf. You can go to eBay right now and have access to any one of these computing platforms. Possibly not the quantum computing. They're quite expensive and considered national technology. So if we take a look at the performance of how these things are doing, so on our x-axis is our power, and we see the y-axis is sort of the peak performance in giga operations per second. So we have different lines representing different types of precision. The idea is basically here to say how much going on in the world of computing, how can we compare them? And so the way you compare these architectures or these compute platforms is you look at how much power versus compute power do they take. And a lot of existing systems on this, operate at rate of like 100 giga operations per watt. Right? So some of the newer offerings, like IBM's True North or Intel's Lohi, falls into sort of bit under these 10 tera operations per watt. So depending on the type of application, you might be okay with a certain amount of peak power. So a lot of machine learning is looking at, you have a problem, you have a data set, how much compute do you need to make sure you're efficiently staying under your budget, but also getting your throughput that you need. So the next sort of big thing that I want to address is robust AI. So what does it mean to have a robust system? So the basic idea behind robust AI that makes it extremely important is that the reason is because of its consequence of actions on certain applications. So we want to measure the consequence of these AI applications in a lot of fields. A very good example is autonomous fields. So the consequence of action of a mistake in an autonomous vehicle can be pretty high. And as of today, the decision making is medium at best, right? So you want people still somehow seem to be okay with fully automating that. So it just shows how the boundaries of these categories can be fluid and subject to societal perceptions and technological advancements. So robust AI plays a crucial role in development and deployment of AI systems. I'd like to just highlight some key features here. So firstly, we have explainable AI. This involves a system being able to articulate its process in an understandable way. Remember, like our loan processing example. If a person got rejected for a loan, you likely want to explain to them why you got rejected for a loan, rather than telling them, hey, sorry, my neural network decided to reject you. Right? So this explainable AI involves a system being able to explain its process. It's not just about the output, so it's understanding how and why you came to that output. And another example would be medical diagnostics, right? So if you have an AI that's doing medical diagnostics for you, you want to make sure that there's a reasoning for why a particular diagnosis came out the way it did. And it might be right, but if it's not explainable, it's not robust. And this particular property of making explainable can be invaluable for the expert learning off of the system. So for doctors, this could actually be invaluable. Next, we have metrics. It's important to have the right metrics. A famous quote from Sam Altman is, you build what you measure. So if you have the right metrics, which is moving beyond just accuracy or performance, you want to consider the right metrics to make sure you're targeting your use case properly. Next, there's validation and verification. Explainability might just be less of a concern compared to if knowing the system just works reliably, depending on your downstream task. For example, let's take automated trading systems. So it's crucial that when certain market conditions are input, the system responds, within like the next couple milliseconds or so, rather than taking like 3 minutes or something like that, because then your market data would be completely different. So next is security. Security is a very vital aspect of these machine learning systems. And it's not just about protecting against external threats, but it's also safeguarding the AI's integrity. Think of it as cryptography for AI. So what this ensures is confidentiality, integrity, the availability of these algorithms, your data sets, outputs, bias, and so on. So you want to make your system robust in a way you're protected against such attacks. And increasingly, a lot of AI have been learned to navigate their way around security systems. And so the natural response to this is to embed AI into your security systems. And so then that becomes just like new field of how do you make something robust in that way. Lastly, we have policy, ethics, safety, and training. This is especially crucial where AI intersects human activities. For example, in autonomous vehicles, policies, and ethical guidelines, these are all essential to determine how these vehicles make decisions in critical situations. To draw an analogy to the gene editing technology that came out a while ago, like there was a there was a ban on it, preventing citizens from using that stuff. And you can draw an analogy to how AI can be thought of as a system that needs controlled usage. So if you were to take away one thing from robust AI, it's basically the confidence level versus the consequence of action, and the scale versus application complexity. So for example, spam filtering, the application complexity is pretty moderate, but the scale is enormous, and this makes it ideal for AI to target. On the other hand, if you have a high stakes corporate decision making, like mergers and acquisition, the complexity is really high, and the occurrences, however, are infrequent. It's not so often. So this is not particularly a target for AI. So I'm going to pause here and ask if there are any questions so far. I'm looking at the chat bot. Okay, I think we're good. All right. So we're going to move on to probably the most important question, or most exciting question, is what is machine learning? That's a good place to start. So how does it compare to traditional programming? So basically, machine learning is the study of algorithms that improve their performance at some task with experience. So in this context, experience would be your data. These algorithms typically optimize based on some performance criteria using example data or past experience. So there are two worlds of learning, supervised and unsupervised. You can correlate these to structured and unstructured data that we looked at before. So in the world of supervised learning, for example, this could mean that you, using the correct label given a input point, can you come up with something that explains that phenomena? So machine learning is a blend of techniques from statistics and computer science, and it's essentially about a computer to get them to program themselves. Common tasks include classification, regression, prediction, clustering, and so on. So for those transitioning from traditional programming to machine learning, here's a useful comparison. So in traditional programming, you have your data, and then you write a program, and then your computer will give you some output. If you see this, do this, and then the computer does that. And you input your data, it outputs some output. Machine learning, however, flips this output in your program. So what you're going to tell you is you're going to give it observations of your data, which is your input and your output. And the computer is going to spit out a program, which is sort of an explanation of how it got from your input to your output. Then you can use your program to then operate on data that is not seen before. And then you would get some new output, which you don't already have the output for. So what are some of these machine learning algorithms? We briefly talked about, we just mentioned neural nets and so on, but what exactly are these? And how does it compare to the work that is being done? So within the realm, we have supervised, unsupervised, and also reinforcement learning. So in supervised learning, you provide labels corresponding to each input feature or data point. And then in unsupervised learning, there are basically no labels, and the algorithm tries to make sense of the data itself. So what that would look like is it would just be data, and a computer would spit out a program. That's what unsupervised learning would look like. Reinforcement learning is, however, quite unique. Instead of labels, you provide it with information, with reward information. So we'll cover this later. So in the case of supervised learning, typical tasks, like I mentioned, include classification, regression, and so on. So we start with some labeled data, often referred to as ground truth, and the goal is to build a model that can predict labels for new data. So there are two main objectives: regression, which involves predicting a continuous variable, and classification, which is about predicting a class or a label. So if you want to build a model that predicts the weather, it is sort of a continuous variable. So that the task you would use there is regression. But if you want to predict, let's say if there's a person in a photo or not, that's a classification task. So here, looking at our diagram, we have our training data, which consists of data and labels. We use this to train some model, typically through some iterative process, and this process helps us evaluate the performance of our supervised learning model. So once trained, this model is then used to apply to new and unseen data to predict labels that you've not seen before. In designing such an algorithm, you want to make sure to separate your training data and your test data. So the key reason is you want to perform a unbiased evaluation of your model. A model that is trained and tested on the same data will likely perform much higher than a model performing on unseen data. So what you can then do with this model is then serve it somehow. So this is typically called inference. So where we use the trained model to do some other downstream tasks. So in a real world scenario, for example, imagine a supervised model trained to recognize different types of vehicles in an image. So during training, it learns from a data set which is labeled, where each image is tagged with either a car, a truck, or cycle, a bike, or so on. And so once trained, you can now give these model new images and ask it what kind of vehicles in the image. So what is vast majority of, or what is the underlying concept of machine learning in the context of artificial neural networks? So I briefly covered these, but neural networks, so to start, there is no class these days that will talk about machine learning without talking about artificial neural networks. So this is a huge part, and this is something that many of you might be familiar with, but basically they've been used for a myriad of applications. So what is a neural network? It's basically a computing system that's inspired by biological neural networks. The system learns to perform some task by training repetitively on some examples. Much of the work that we've seen typically applies to supervised learning. Also, there's some growing research towards using them for unsupervised learning. So the components include input, layers, output, and weights. So these are terms you will hear if you're in the field of machine learning often. So there are different types of these neural networks. So there's deep neural networks, which is networks that have more than one layers. So a layer is what you see right here. So this would be one layer. So you have your input layer, you have your output layer, and you have some hidden layer. So a deep neural network, as opposed to a shallow one, has multiple hidden layers. And when I say multiple, it's usually on the order of like hundreds. So it's also about the complexity and capability of your network to model these high-level abstractions. So for example, given a downstream task like image recognition, deeper layers might identify more complex features, like shapes or specific patterns, and how these simpler patterns build to form the bigger image. So that's the reason you have different class of neural networks, because some fit your downstream task better than others. And this is a huge subsection of machine learning, is how do you pick the right hyperparameters, the right number of hidden layers, the right number of neurons, and so on. And this is something that is currently being explored as a search space. So basically you define that these are all your possible options. Can you try and find me the best layout for my task? So this is analogous to the chess example I mentioned earlier. This is probably the best way of doing it. Although current research there's a lot of guided research towards embedding knowledge into picking how you can model the right number of hidden layers, input layers, or output layers, but this is still growing research. So within these classes, there's multiple variants. So the first is a convolution neural network, which are particularly good for image processing. And we have recurrent neural networks, which are excellent in handling sequential data, like speech or text. We also have deep belief networks, which are effective in handling unsupervised learning scenarios. So one reason these networks are really popular is the accessibility. So nowadays you can go online and in about 5 minutes you can build your first neural network. So the accessibility has just exploded. In contrast with more traditional modeling like hidden Markov models, which might be very unintuitive and difficult to implement for beginners. So making it accessible has made it quite popular. So looking at a step further, let's look at a deep neural network in a bit more detail. So we start with some input features, which could be anything like, let's say you're looking at an image, right? These could be an RGB pixel value for each of your image. So let's take a 4x4 image, or let's take a 2x2 image. So this is just an image with 4 pixels. And let's say each pixel has a 2 color values to it. So what you would do is you would take this and just lie it out. So we have total 8 sort of input, and if you were to lie it down into a single row, this is what it would look like. So what you do then is you have multiple hidden layers, and you take your input and you multiply it by some weights. So capital W0 is your weights of your first layer. P0 is the bias associated with this, and you define these for each of your layer. So the math basically looks like you get your next layer by multiplying the weights of your previous layer to some features, and you add your bias. So this might look like any sort of like linear system to you. So, but really the F is sort of the key thing here. We take your input, we model it through some weights. So what makes this a neural network is really the W's here. So each iteration, we give it an image, we get an output, and depending on how far away our output is from our label, we adjust these W's. So when you adjust these W's, they become closer to modeling the phenomena that governs the transformation from your input to your output. So I mentioned a bit about what these input features could look like, but more examples are, let's take a facial recognition software. The feature might include, the distance between key facial landmarks in addition to these pixel intensities. So if you're trying to classify if a person is the given person of interest, you would input all this information about them, like how far their eyes are, maybe how far their nose is from their chin, things like that. So these are things that you can observe using some given medium like sensors or labels from people. So the core of this process is quite simple, right? It's at the base, it's just linear algebra. So the output layer also follows some nonlinear activation after you have your hidden layer. This is basically to prevent some sort of exploding outputs. So let's just take one of this neuron right here and make it bigger. So that's what this would look like. So you have your input coming in from your previous layer, right? So this is what it would look like. Take some values. Let's call this y sub I. So the different weights would be like W1, W2, W3. And so what you would do is you would take your input. So in this case, what f would be is, oops. So you have negative 0.06 times W1 plus 2.5 W2 plus 1.4 W3. That's essentially what you're doing, right? So then you pack this to some activation function. Activation functions can be thought of like a bounding function, which basically keeps your values within a certain threshold. This is specifically useful when you're thinking about a downstream task. So let's say you're trying to classify whether it's a dog or a cat. A given image is a dog or a cat. So 0 would be a dog and 1 would be a cat. And once you perform your activation, you can think about how close your image is to a dog rather than a cat. Of course, it doesn't mean anything logically to be 66% cat, but in machine learning, it just means that the image that you've given me is 66% likely to be a cat. So this is called their nonlinear function. So in this case, it's a sigmoid function, which is a very common activation function used in neural networks. And applying this to our value, we get a value that is bounded by 0 to 1. So you take this thing and you do this repeatedly. So our W here is a matrix, but which consists of like n1 by n2 entries. So this is a lot of computational expense. So now this motivates our architecture that we looked at before. So looking at this, people go, okay, there's a lot of optimizations that is not being encompassed in current architectures. And so people come up with TPUs, people come up with neuromorphic computing, and people come up with graph processors, and things like that. So what makes this machine learning is you update these W's after measuring how close your output is. So let's say this outputs 0.3, but in reality you want a 1. So it tells you your image is 30% dog, but your image is a dog. So you want to adjust your weights so that the output of this network is closer to a 1. So real neural networks can have thousands of inputs, hundreds of layers, and undergo millions to billions of weight changes per iteration. So there's significant work in parallelizing this process. Traditionally, it's a serial process, but there are techniques for distributed processing. Quite a bit of my research actually involves working on distributed machine learning. So one such technique is model parallelism, where the model is distributed across multiple processors, then we adjust it simultaneously. So for example, what that would look like is, let's say you have a deep neural network, you put the first 2 layers on one device, you put the second 2 layers on the second device, put the last layer on another device. That's essentially what it would look like. That's what model parallelism is. Data parallelism is where all machines have the same copy of your neural networks. And then what you do is you split your data set to multiple machines. So each machine can independently run some set of inputs to get some outputs. Of course, there needs to be some communication between these devices to make sure you're updating your weights in a synchronized fashion. So inference involves using these trained models and the power of their nonlinearity, right? So the nonlinearity that we looked at here allows them to classify and predict complex patterns that linear models can't handle. So for example, if you have a simple classification task, a linear classifier might be enough. But in a more complex pattern, a neural network's capability to identify intricate decisions are made possible because of your nonlinearity. So when you design your neural networks, you want to be aware of the depth and the number of layers and input trees and so on. So let's take a look at like a visual example of why nonlinearity is so important. So if you had just a linear classifier, and if you had your data points looked something like X's and O's that were laid out in your feature space like this, if all the X's represented cats and zeros represented dogs, this would be fine. But for data that's more complex, you want to make sure you can model this properly. And the way you do that is just using your nonlinears. So that's why nonlinears there's a lot of research going on into picking the right type of nonlinear activation functions. This is pretty interesting. So when you design a network, there's a lot of hyperparameters that you have to consider. So the number of layers, the number of inputs, the network types, the layer types, the training algorithm, and often due to the cost of training, many start with existing models and they just sort of adjust their weights from there. So unsupervised learning is about finding the hidden structures in its unlabeled data. So this is used for clusters, data projection, dimensionality reduction. So this is a whole class of machine learning networks that would fall under, that would increase your search space by a couple orders of magnitude. So in supervised learning, we basically had some data and then we had a label telling us what data that was. But in unsupervised learning, we're just telling it, hey, here's my data. Can you give me some sort of patterns that you identify in this? And a typical task is clustering, data projection, and so on. So what are clustering, right? So let's say you have you're interested in where people gather in a given university or something like that. This information would be useful to a campus that plans on constructing some facility that's most convenient to where the students convene. So you give it locations of all the students throughout the course of time, and you ask it, hey, what are some patterns that you notice? So this task would somewhat be unsupervised learning. So our goal in unsupervised learning is to discover interesting things about our data sets. Are there any subgroups, patterns, or clusters? So if you're doing a user survey and you collect about 1,000 responses for people in your program, you can sort of do some unsupervised learning and see what your target distribution looks like. So how many people are doing this in their 30s? How many people are in their 40s? How many people are in their 20s? And this is sort of interesting things to look at. So basically, we want to group a set of features that are in a similar cluster rather than another cluster. So remember, what we do is we take our input and we adjust our weights in a way that it matches our output. So that's what supervised learning looks like. So in unsupervised learning, what you try to do is you adjust your boundaries so that you minimize your loss function. So loss function is some criteria that you have, and you want to bring this closer to as little as you can. So what's happening here is we're minimizing the distance that an object is with a certain cluster as opposed to another cluster. So that's what the MI is. MI is basically the mean of all the features in some given cluster I. So for all the clusters, we are across all data points, we are minimizing the distance that it belongs to some certain cluster as opposed to the mean of another cluster. That's basically what this equation is saying. Another interesting neural network architecture is autoencoders. Autoencoders are an example of unsupervised learning. So our goal here is to compress data and then reconstruct it. So the metric here is a difference between the image reconstructed output in aiming for minimal loss during compression. So why is this useful? There's a lot of like style transfer that's going on in machine learning right now. What you can do is you give it some input in a domain A and you want it to reconstruct it, say in domain B. So let's take seismic data, for example. So we have seismic data that consists of two types. Let's say there's like acoustic data and there's also like elastic imaging. So if you have one, the other might be really expensive to construct. So you learn a model which maps one to the other, and now you can use that model to map acoustic data to elastic without being able to like go out in the field and collect new data. And this makes it very cost efficient as opposed to collecting the data in the field. So moving on to reinforcement learning. And reinforcement learning is different from supervised and unsupervised learning. Basically, it involves learning through sort of like rewards from interactions with an environment without explicit labeling. This is useful in complex and dynamic scenarios, like training a robot to navigate obstacles. So if you see those videos where you have like these robots learning some complex movement, this is probably reinforcement learning. And so what they do is they try to maximize the reward that the system earns during the course of its training. So it mimics human learning and it encourages the algorithm to repeat actions that yield positive outcomes. So for example, you're training a robot to walk. Every time it falls, you give it some negative reward. You penalize it. And if it does something well, you give it a reward. And it would adjust its weights, the big W's that we saw, so that it maximizes the reward, or maximizes the actions that lead to the reward. Some examples here are like playing Atari, which is basically a game, and reinforcement learning was trained to do this. And also, if you played video games, stuff like Dota and things have been highly targeted by machine learning community. So there's some other examples of reinforcement learning where you can train a sort of a drone to do some stunt maneuvers where you reward it if it follows the desired trajectory, or you penalize it if it crashes. And so the next run, the drone's going to adjust its hyperparameters so that it can, maximize its reward. Managing an investment portfolio where you reward it each time you earn $1, and you could penalize it for each time period that it does not earn $1. Something like that. So make a humanoid robot walk. That's the example we looked at. So this is what reinforcement learning in a nutshell is. So we looked at like three broad views. So we looked at supervised, unsupervised, and reinforcement learning. It's all great, but there's also a lot of issues that we run into. So let's look at the issues quickly. So some very common ML pitfalls are overfitting versus underfitting. So imagine you're developing a model that performs exceptionally well on your training data. However, when you apply it to your data set, the results are extremely disappointing. So the discrepancy often arises because the model is overly tailored to your training data, and this lacks its ability to generalize to more newer data. Another pitfall could be the choice of algorithm. Sometimes your algorithm might not be capable of accurately modeling the behavior shown by your training and test data. For instance, if your data exhibits a very complex nonlinear relationship, you've chosen a linear model, the model is not going to do well. Right? So data quality is also another critical factor. You might end up with the algorithm that's amazing and good compute, but if your data is not good, you might just get poor results. And this is really hard to debug because it's very likely in the traditional way that your algorithm is much worse and not your data. So you want to make sure to follow good data quality practices. These are pretty important features. So I've listed some other ones here. So you have model selection in this huge search space, not having good success metrics, ignoring outliers, training versus test data, correlation versus causation, and so on. So if I were to train a machine learning model that tells you, that gives you some correlation between two feature spaces, that does not imply causation. And so you might be modeling variables that only imply correlation but not causation. And ignoring outliers actually quite a mistake, because there's cases where you have anomaly detection. For example, let's say you're watching Netflix and there's anomalies of different shows that are being suggested to you. So these are cases that you do not want happening. Okay, so moving on to what's actually really popular now is these language models. So these language models are huge. So we're starting to see models that are on the order of billions of parameters. And everyone's really excited about ChatGPT and so on. So I'm just going to quickly cover what composes of these models. So the goal of a language model is essentially to model some probability distribution. So you see ChatGPT, you input some prompt to it, and it gives you a response. What it's trying to do is it's trying to maximize the probability that its answer is in response to your question. So any model that computes either a probability is a sort of a language model. So we have a regressive language model training here, which basically, given a sentence, it's going to try and compute the probability that the sentence is the actual English sentence. And this trains to do that by looking through a corpus of your data. So language models are quite popular and quite capable. What they can do is for example, you can tell it to predict the sentiment of a given sentence, and without training on any sort of data distribution before, it can give you sentiment prediction. And sort of these are things that have been made possible due to the huge language models that we've seen so far. Here are some examples of future generation, where we see, we give the model some examples of input and output that are expected, and then you give it some random input, and it tries to predict an output based on the examples that you've just given it. And these models are never trained to detect sentiments or detect sarcasm or generate summaries, unlike our supervised tasks. It was simply trained to predict the next task. And so we have huge amounts of data with a lot of parameters that need to be tweaked for this. So this is also pretty unsafe, right? So a lot of people assume that GPT knows stuff. In reality, it does not know anything. All it's trying to do is just maximize the probability of your next sentence. So which brings me to a key point, is you cannot use LLMs for search, at least not by itself. What you can do is you can embed your knowledge base as some sort of embedding and use that to power your language models. So what that means is you type in a query, it finds all the documents that relate to your query, pass that to the language model and be like, hey, this is my knowledge base. Can you answer this question based on your knowledge base? So that's a key way that companies like Google, Amazon, OpenAI are using language modeling for search as of today. So language models for search was the end of 2019. What's up in 2023? And we've seen increasingly more importance in language models for things that have been existing for over 2 decades. For example, Uber, Maps, and also this company called You, and there are whole companies that are being built that are geared towards these language models. And there are several risks that are related to these. First is they're not reliable, right? Since they're just predicting a sentence that matches to your output, they're very unreliable. They have a lot of social bias. We see this example where you say king, queen, father is to mother, male is to female, and doctor is to nurse. And this is not true. And when you ask it to generate hypothetical casual conversations, there's a lot of bias that's sort of inherent to these conversations. And also disinformation is a huge part. You do not want to rely on this stuff for scientifically accurate information. And privacy is where you have your data corpus, which consists of sensitive information, and you don't want to be able to extrapolate these from your inference. So you don't want to pass a prompt and then retrieve all the private information that it was trained on. Lastly, we have, a legal consideration, and there are increasingly a lot of cases against artificial intelligence, and this is just another reason that a lot of companies have been popping up to address these issues. So the reason I'm mentioning these risks is essentially this provides a lot of opportunity to be able to improve in different directions. So that's the summary. There's a lot of exciting research going into these machine learning techniques, data availability, compute, and so on. So that's all I had. Thank you very much. If you guys have any questions, I will take them now.
Yeah. Thank you, sir. Thank you, Mr. Rexami, sir, and Mr. Richard, sir, for delivering an outstanding presentation on the topic machine learning techniques, trends, innovations, and real-world applications. You have dealt on artificial intelligence, AI canonical architecture, different types of data used in AI, machine learning algorithms taxonomy, modern AI computing engines, importance of robust AI, and other machine learning techniques. Dear participants, if you have any queries, you are invited to ask your queries and clarify your doubts. If you have any queries, you can post them in the chat box or raise your hand to ask for questions. So, if there are no further questions, I would like to propose a big thanks to today's resource persons. Sir, a special thanks to you for taking interest, waking up early morning at 4:30 to start your session. It is really a boost, especially for me, for spending your time to share your knowledge.
Yeah, this is really exciting for me as well. So thank you for the opportunity.
Yeah, yes. It shows your interest to share your knowledge. Your valuable thoughts and insights have enriched our understanding of the subject. And we truly are grateful for your generosity in sharing your expertise with us. Thank you once again to both of you, sir. Thank you.
Thank you.
Now let us continue with the valedictory session.
Let's continue with the valedictory session. I would like to invite Dr. Sister Amul Mary, the convener of the seminar, and 1 week Webinar-cum-FDP to present the report.
Thank you, Dr. Vimala Devi. I, Dr. Sister Amul Mary, the convener and head of the Department of Computer Science, would like to give you the glimpse of the report of 1 week International Webinar-cum-Faculty Development Program on recent advances and future trends in artificial intelligence and cyber security, held from 14th November to 20th November 2023. This 1 week webinar focused on exploring the integration of AI technology into teaching and learning process. This FTP brought together faculty members, research scholars, students, and external participants to discuss the possibilities and potential of AI in education. All the sessions featured dynamic presentations on incorporating AI tools in classrooms for faculty members and the current state of AI tools investment in the world. On the first day, Professor K. Gangadhar Rao, HOD of Department of Computer Science and Engineering from Acharya Nagarjuna University, delivered keynote address. Dr. Arun Yanaraj, Software Project Manager, shared his knowledge on topic Insights into Integration of AI and Machine Vision Applications and Advances. Professor Vimal Gerald on the second day dealt on AI for smart teaching, learning and evaluation, a demonstrative session. Dr. K. R. Manchula on the third day from Sastra University dealt on role of data science and AI in cybersecurity. Dr. P. Tejasvi, Assistant Professor from VNR Engineering and Technology on facial recognition using deep learning, and Mr. Ravi Kant on demonstration of Tableau tool for data visualization. Dr. Krishna Prasad, Professor and HOD of Cyber Security and Cyber Forensics from Srinivas University, Karnataka, dealt on various AI tools used for research methodology. Dr. J. Rexy, Coordinator and Assistant Professor from St. Xavier's College, enlightened us on power of artificial intelligence in digital era. And today, Dr. Rex Aragasamy and Mr. Richard Rex from Georgia, United States, on the topic machine learning techniques, trends, and innovations in real world applications. This whole week was a learning experience for all of us, getting to know about cybersecurity and different artificial intelligence tools with practical knowledge. Every day, the session started with a welcome note and speaker presentation for 2.5 hours, followed by 15 minutes of interaction. The session continued for 2.5 hours. A short feedback session also was conducted. Around 150 participants registered and participated in this webinar, International Webinar-cum-Faculty Development Program.
Thank you, sister, for your wonderful report. Now, we shall proceed to the end of the session. That's expressing gratitude for the success of the webinar. I should first thank and convey my deep regards to our honorable eminent speakers. I should first thank and convey my deep regards to our honorable eminent speakers, Professor K. Gangadhar Rao from Acharya Nagarjuna University, Professor Vimal Jaral, St. Joseph's College, Dr. K.R. Manjula, Sastra University, Dr. P. Tejasvi and Dr. Ravikant, VNR Engineering and Technology, Dr. Krishna Prasad Srinivas University, this is Dr. Krishna Prasad Srinivas University, Dr. J. Rexis St. Xavier's College, Dr. Rex Arokiswamy and Mr. Richard Rex, who spared time from their busy schedule to grace this one-week FTP with their extremely relevant address. We have no words to offer gratitude for your motivation and inspiring thoughts. We are ever grateful to you for your impressive and lively sessions. Your interaction with the participants was really outstanding. My sincere gratitude to management, Dr. Sister Teresamma Gade, the correspondent Dr. Sister Shaini, the principal, for being a constant motivator and guiding force in all our endeavors to organize this webinar. A big thanks to Sri P.S. Surya Prakash Rao, Joint Secretary to Governor Andhra Pradesh, for his valedictory address. I express my sincere thanks to the IQAC members of the college and committee members, Mrs. Karimunisa, the coordinator of the webinar, Mrs. Yojita, Dr. Vimla Devi, Dr. Jyoti Valivia, Mrs. Arunodaya, and Mrs. Sanuja for your relentless efforts in making this webinar a grand success. I would like to thank all the participants, principals, university professors, faculty members, research scholars, and students who participated in this Webinar-cum-FTP. I convey my sincere thanks to Mr. Srikanth for his technical support. Once again, a big thanks to all of you wholeheartedly for glorifying this one-week international Webinar-cum-FTP. Dear participants, as we conclude this enriching day, I would like to make a few announcements that feedback form is sent to the WhatsApp group and chat box. You are requested to fill the feedback form. Your feedback is invaluable. All those who registered, attended the webinar and filled the feedback form will get e-certificates to your registered mail ID very shortly. Once again, I express my sincere thanks to each one of you for your active participation, making this webinar effective and successful. Have a wonderful evening. Thank you. Thank you, one and all.